Hello. So in last lecture we discussed about the boundary condition for electric wave. So in boundary condition for electric wave we have to consider total three types. First, medium 1 is dielectric, medium 2 is dielectric, medium 1 is dielectric, medium 2 is conductor, medium 1 is free space, and medium 2 is conductor. Okay, so we have already discussed these two cases. Now in today's lecture, in today's class, we have to discuss about this one. If medium 1 is free space and medium 2 is conductor, then what is the boundary condition? Okay, so again, what is boundary condition? So suppose we consider this one is my medium 1, medium 2. This one is a electric wave, okay, which is propagating in this direction, and this one is my transmitted wave. Okay, so it's an incident wave and transmitted wave. Medium 1 and medium 2, incident wave and transmitted wave. So in boundary condition we have to derive a relationship between the tangential component in boundary 1 and boundary 2 and normal component in boundary 1 and boundary 2. Okay, so now today we start these three. If medium 1 is free space, means this medium, if medium 1 is free space and medium 2 is good conductor, then what is the boundary condition for electric wave? Okay, so now we will take here, suppose this one is the boundary which is separated two medium. Okay, so this one is my first medium, medium 1, which is free space. Free space means it is air medium. And what is a relative permittivity for the free space is unity 1. And second medium is conductor or good conductor. Okay, so by our knowledge we know that no electromagnetic field or no electromagnetic wave propagate in the good conductor, because the good conductor has a very high conductivity. Good conductor has very high conductivity, approximately infinity. So loss in the good conductor is infinity. So there is highly loss in good conductor for electromagnetic wave. So we can say that no electromagnetic wave is present in good conductor. Okay, now suppose here E1 is my transmitted wave. Okay, E2 is my, okay, E1 is incident wave, E2 is transmitted wave, but no field is present in good conductor. So actually all the wave is reflected back. Okay, no, okay, see, this wave is known as incident wave. Whatever the wave is entering into the second medium, it is transmitted wave, and some of the wave is reflected back, it is known as a reflected wave. Okay, so in good conductor there is no electromagnetic wave is present. So whatever the wave is incident, okay, the same amount of wave is reflected back. Okay, we will discuss this topic, what is reflection coefficient, what is transmission coefficient, in our next lecture. Okay, so now this even has a two component. First is normal component and second component is tangential component. Okay, we'll do the same analysis that we have to do in a previous case. Okay, I will take one closed line and this one is indicate the direction of closed line. Okay, so first of all we have to find out the relationship for the tangential component. So how to use Maxwell equation, which is integration E into dl is equals to 0. How to split this equation into the total 6 parts. First is for A to B, A to B, B to C, plus C to D, next D to E, E to F, and final F to A is equals to 0. Okay, so this one is width, which is delta W of this loop, and height is delta H. Okay, so now I do the first calculation for the A to B. Okay, so E1T is in the same direction. Okay, so here it is E1T delta W. For B to C it is E1N delta H by 2 plus C to D. No component is present. Okay, so here it is 0 plus D to E, no component is present in the second medium, so it is 0. Similarly, E2F, no component is present in the second medium, so this 0, plus F2E is in the opposite direction of E1N, so this minus E1N delta H by 2 is equals to 0. These two components are totally cancelled out. Okay, actually this calculation is the same calculation that we discussed in last class. Okay, so the tangential component is 0. That is why d1t is also 0. So, okay, so electric field intensity, tangential component for electric field intensity is 0. So tangential component for electric flux density is also 0, because d is equals to epsilon E. Okay, so it's a relationship between the tangential component. Okay, so if the wave is incident wave, okay, if the wave is incident at the boundary and if the second medium is a conductor, so value of E1t is equals to 0. No tangential component is present at the boundary. Okay, next for the normal component. Okay, now we do the calculation for the normal component. Okay, so again consider this boundary, first medium, free space and good conductor. Okay, now here it is d1. So this d1 has a total two part. First normal component of d1, second is tangential component. Okay, we have to use Maxwell equation, integration d into ds is equals to q. Here it is ds means it's a closed surface, so we have to take a cylinder has a closed surface, and this cylinder has total three sides. First is top side, bottom side and side wall. Okay, so AN is the direction of top side, this AN is the direction of bottom side. What is the area of the top side? Delta S. What is the area of the bottom side? Delta S. Okay, so I have to divide this integration into the three part. First is top, second bottom and integration side wall. Okay, is equals to q. Okay, for the top side integration, which component is in the same direction? d1n. Actually it is in the opposite direction, so the answer is negative. Okay, so this minus d1n delta S. What about the bottom side? There is no field is present in the second medium because the second medium is conductor, so it is 0 and side wall is also 0. Okay, so this minus d1 n delta S is equals to, I have to apply the surface charge density constant, which is rho s into delta S. So here d1n is equals to minus rho s. Okay, and at the surface of course the charge is present. Why? Because it is a conductor and conductor contains some charge. Okay, so here at the boundary or at the surface the charge is always present, so d1n is equals to minus rho s. Okay, so this one is a boundary condition for electric field or electric wave when first medium is free space and second medium is good conductor or conductor. Okay, so what is the final conclusion? The final conclusion is here the tangential component is 0. The tangential component for electric field intensity is 0, but the normal component is not 0. Okay, that means if electric field is incident at this, okay, is incident at the boundary, and if the second medium is conductor, so this tangential component is 0. Only which component is present? Only and only normal component is present. Okay, and all the wave is reflected back because no wave is transmitted inside the good conductor. Clear? So these are the boundary conditions for electric wave. Okay, so here we have to consider three cases. First, medium 1 is dielectric, medium 2 is dielectric. Second, medium 1 is dielectric, medium 2 is good conductor. Third, medium 1 is free space and medium 2 is good conductor. Okay, so these are the boundary conditions for electric field. Next, our next question, which is boundary condition. Okay, our next question is, next subtopic of this chapter, explain boundary condition for magnetic wave. Okay, so actually in this topic we have to take two different medium again. but we consider both the medium is only dielectric medium. Okay. Again, we don't consider these three different cases. We consider medium 1 is dielectric and medium 2 is dielectric, nothing else. Okay, clear? It's not dielectric actually, but we consider there are the two separate medium. Okay, they are not dielectric because electric medium is used for the propagation of electric field only. Okay, so that is why the name is dielectric medium. Okay, we consider only two different medium. We don't consider the conductor, we don't consider the free space, we consider just two different medium. Okay, so now next question, the question may be asked in this way: explain boundary condition for magnetic field, or explain boundary condition for magnetic wave for two different medium. Okay, so here we take boundary which is separate two medium, first medium and second medium. First medium has permittivity, permeability. Now it is a permeability which is mu r1. Second medium has a permeability which is mu r2. Okay, now here is the wave, and now this wave is magnetic wave. Okay, the wave is magnetic wave. So first of all, suppose it is b1 vector. Okay, and this transmitted wave. Okay, so incident wave, transmitted wave is b2 vector. Okay, and it has a two component. First is normal component which is b1 and second is a tangential component b1t. Okay, similarly for the second medium, here it is b2 and normal component and b2t tangential component. Okay, so we have to use Maxwell equation for magnetic field. Okay, so here we have to apply Maxwell equation: integration b into ds is equals to 0. Okay, for normal okay, first we do the calculation for the normal component. So this integration b into ds is equals to 0. So it's a closed surface. Okay, so I have to take a closed surface. Okay, here first we do the calculation for the normal component and then tangential component. Okay, in the remaining case, okay, in all the previous case we do the calculation for first the tangential component then normal component. Okay, but first we do the calculation for the normal component. So it's a closed surface. So this closed surface, this cube has total 3 sides: top side direction, bottom side direction. What should be the area? Okay, so here area is delta S, this area is also delta S. Okay, and this one is a side wall. So now I do the calculation. Okay, so this is top side calculation plus bottom side calculation plus side wall calculation is equals to 0. Okay, top side integration, bottom side integration, and side integration. Okay, so for the top side, which component is in the same direction? b1n is in the same direction, and it is actually both are in the opposite direction. Okay, so we can write minus b1n delta s. What about the bottom? b2n and an both are in the same direction, so b2n delta s. What about the side wall? It is 0, is equals to 0. Okay, so we can say that the normal component b1n is equals to b2n. So normal component for magnetic flux density are same, but b is equals to mu h. Okay, so put here is mu 0 mu r1 h1n is equals to mu 0 mu r2 h2n. Mu 0 are cancel out. Okay, so mu r1 h1n is equals to mu r2 h2n. Okay, so here normal component for magnetic field intensity is discontinuous, but the normal component for magnetic flux density are continuous. Continuous means whatever the component is present here, whatever the value of this component is present here, the same value is present in the second medium. Okay, so this is known as the continuous. Okay, see here, for example, suppose B1n vector has a value 10. Okay, so the same value is present in the second medium, which is 10. Okay, so it is known as a continuous component. Okay, so this type of the component is known as a continuous component. Okay, so B1n is equals to B2n. So normal component for magnetic flux density are continuous, but the normal component for magnetic field intensity is discontinuous. It's not continuous. These two components are not same due to different μr1 and different μr2. Okay, so here we do the relationship between normal component. Now what about the tangential component? Okay, so now we do the calculation for the tangential component. So again I will take boundary. Okay, medium 1 μr1, medium 2 μr2. Okay, now what we assume, the wave is not B1, now it is H1 vector, and this wave is H2 vector, incidence wave and transmitted wave. Okay, it has a two part, H1 and H1t. Okay, similarly for this case, this H2n and H2t. Okay, now in this case we have to use Ampere Second Law, which is also a Maxwell fourth equation, which is integration H into dl is equals to I enclosed, okay, or current I. It's a closed line integration. Okay, so we have to consider a closed loop. Okay, we have to apply the same concept that we have to apply in the electric wave. Width and height. So this one is the width of the loop, delta W. This one is the height of the loop, delta H. This delta H by 2. Okay, this one is delta H by 2, and this one is also delta H by 2. So the total height is delta H. Okay. So now it is okay, A to B, B to C, C to D, D to E, okay, E to F, and F to A is equals to I. Okay, now A to B. What is A to B? Okay, so this one is the direction that we have to choose. Okay, A to B is in the same direction of H1t. Okay, so this H1t delta W, length of A to B is delta W, plus B to C, length of B to C is delta H by 2, is in the same direction of H1n. So H1n delta H by 2 plus C to D is in the same direction of H2n. Okay, so H2n length is delta H by 2 plus next D to E. D to E is in the opposite direction of H2n, so minus H2n, and length is delta W, and E to F. Okay, so in the opposite direction of H2n, so minus H2n delta H by 2, and last is F to A, which is minus H1n delta H by 2 is equals to I. The total current I enclosed. Which part are cancelled out? This part are totally cancelled out. Okay, so we can write delta W H1t minus, okay, it's T, H2t is equals to I. Okay, so delta W into H1t minus H2t is equals to I. I means that the total current enclosed. Okay, so now here we apply the concept of surface current density. Okay, see here, this one is a surface. Okay, actually it's a boundary which can separate first medium and second medium. Okay, but at the boundary the current is flow in any direction. Okay, the current is flow in any direction. And see here, here we have to apply the Ampere circuit law. The Ampere circuit law say that the closed line integration of magnetic field intensity is equals to I enclosed. Okay, so we have to choose a one Amperian path that we have already discussed in our lecture. Okay, what is Ampere circuit law? What is Amperian path? Okay, how to choose a Amperian path? Your Amperian path must be a closed path. Okay, it may be in any shape. Okay, either a circle, square, triangular, but the condition is your path must be a closed path. Okay, so this loop is nothing but we can consider is one type of the Amperian path. Okay, so this one is a surface. Okay, this one is a surface and the current is flow through the surface. Okay, see here, actually I have to draw this surface in a 2D paper. Okay, but consider, suppose this one is a 3D. Okay, so this one is my surface. Okay, this one is this total surface. Okay, you can assume in this way, this one is my surface. Clear? This one is medium 1 and this remaining is my medium 2. Okay, and the current is flow through the surface. Now the main thing is, what is the direction of current that is flow through the surface? Okay, so suppose if I have to consider this one is my surface, so the current is flow in any direction. The current is flow in this direction, the current is flow in this direction or in this direction, or the current is flow in the surface. That means the current is flow in this upward direction of the surface or in the downward direction of the surface. Okay, so how can we define the direction of the current? Okay, so we have to apply this Amperian path concept. Okay, so here the Amperian path is, okay, if you look here, the Amperian path is a clockwise path. Okay, the Amperian path is a clockwise path. So if we apply the screw concept, okay, so if the clockwise path, so screw is inside this board, screw is inside the pitch. Okay, if I have to wind in this direction, okay, so screw is go inside this pitch. Okay, so we have to consider the current is flow inside this page throughout the surface. Inside the page the current is flow. Okay, so actually this one is the direction of the current. Okay, so this cross is indicate the current is flow inside the page throughout the surface. The current is flow throughout the surface, but the direction is inside the page. Okay, clear? So here the current is present inside the page direction throughout the surface. Okay, so we have to apply the surface current density concept. Okay, so what is surface current density? So here the surface current density, which is denoted as K. So K is equals to current upon, I have to choose only this loop. Okay, now see here, the current density is depend on what? The current density is depend on delta H or it depends on delta W. See here, suppose I have to stretch this loop. Okay, I have to increase the, okay, try to understand, if I have to increase delta W, okay, if I have to increase delta W, that means the length of this loop is more, so the more current is passing through the loop. Clear? And second case, if I have to increase the height of the loop, then what about the current? The current remains fixed. The current is not, okay, not increased or not decreased. Okay, because I have to just increase the height of the loop. But if I have to increase the width of the loop, so more current is passing through the loop. Okay, so here this current density is depend on only delta W. Okay, so it is K is equals to I upon delta W. Clear? So K is known as surface current density. Okay, so I have to put this value here. So H1T minus H2T is equals to K. Okay, where K is known as surface current density. Okay, Clear? So this one is the relationship of tangential component. Okay, but we know that B is equals to mu H. So H is equals to B by mu. So put here B1T by mu R1 minus B2T by mu R2 is equals to K. Okay, so no tangential component for for magnetic field intensity or magnetic flux density. No tangential component is continuous. It depends on what? It depends on the surface current density. Okay, it depends only and only the surface current density. Clear? Now see, we have to find out the direction. Okay, see here, this H1T minus H2T is equals to K. Okay, I have to write as a scalar quantity, but if I want to write as a vector quantity, then what we have to do? So this one, okay, so I'll write this equation again. So in terms of vector, H1T vector minus H2T vector is equals to K vector, because surface current density is also a vector quantity. Okay, what is the direction of H1T and H2T? This one is the direction of H1T and H2T. Both are in the same direction, H1T and H2T. What is the direction of surface current density? The surface current density is in this same direction of the current. Okay, and the current is inside the page, so the surface current density is also inside the page. Okay, so these two directions are not same. Okay, H1T minus H2T and K direction are not same direction. Okay, so what we have to do actually? So here we have to do cross product of this term with one extra term. Okay, that the answer is exactly equal to K. Okay, so here we have to apply cross product concept. Okay, and something is left here. Okay, so we have to do the cross product of this quantity with one unit vector. Okay, so it's a very small assignment. You can find out. Okay, you can find out this unit vector by yourself. We have to multiply with which quantity. Okay, we have to multiply with which quantity? With H1T minus H2T, so that if we do the cross product between these two vector quantities, so we will get the same direction of K. Okay, clear? So it is all about the magnetic boundary condition. Okay, so we will quickly revise what we have to do. The magnetic boundary condition. In magnetic boundary condition, okay, we have to take the first case. We have to find out the relationship between the tangential component and normal component. First we have to find out the relationship between the normal components. So the normal component are continuous, but the tangential component is not continuous. It depends on the surface current density. Clear? Okay, so now in next lecture we will discuss about the reflection of uniform plane wave, which is known as UPW, uniform plane wave at normal incidence. Okay, thank you.